Hello, y'all. Darrell Berry Jr. here, back for some more physics. We'll be reading about the Coriolis force in section 9, section 10, 410 of a graduate textbook. So this is 410, the Coriolis effect. And I'll get through the entire section and then call it a day, as I'll have my session early today rather than at the regular time. Let me change the text here. Equation 4.86. So let's go to 4.86. Keyboard there. Probably easier at this point just to scroll in the book. So that's 4.86. This is the change in the space coordinates equals the change in the body coordinates plus the angular velocity of the particular axis that is being rotated around times the position coordinate. I have to clarify a bit what the x is. Oh, so x is a vector that this is being applied to. Equation 4.86 is the basic kinematical law upon which the dynamical equations of motion for a rigid body are founded. This basic kinematical law, from that you get the dynamical equations of motion. What's going on, Aaron? Thanks for saying. I appreciate it. Thanks for dropping a line. Let me know if you have any questions or comments. It may be used whenever we wish to discuss the motion of a particle or system of particles relative to a rotating coordinate system. All right. Got it for rotating coordinate system. Particularly important problem in this latter category, the rotating coordinate system, or system of particles, is the description of particle motion relative to coordinate axes rotating with Earth. Recall that in section 1.1, an inertial system was defined as one in which Newton's laws of motion are valid. Okay. Inertial Inertial means Newton's laws are valid. For many purposes, a system of coordinates fixed in the rotating Earth is a sufficient approximation to an inertial system. However, the system of coordinates in which the local stars are fixed comes still closer to the ideal inertial system. Detailed examination shows there are observable effects arising from Earth's rotation relative to the nearly inertial system. Equation 4.86 provides the needed modifications of the equations of motion relative to the non-inertial system fixed in the rotating Earth. Okay. So seems like they're saying we have Earth rotating here, and we can make a coordinate system in the Earth, fixed in the Earth, and it's basically inertial, but Earth is moving relative to the local stars. So now we have a relative to stars non-inertial. So we have to use 4.86 to adjust the equations of motion relative to the stars. Because for instance, if I move from here to here on the Earth, relative to the Earth, I can say it's inertial. But since the Earth is moving relative to the stars, really there's other motion going on. Relative from the perspective of the stars, you move differently than how you moved in that little distance. And the adjustment of equation 4.86 will give us that, is what I'm understanding. The initial step is to apply equation 4.86 to the radius vector. The initial step is to apply equation 4.86 to the radius vector r from the origin of the terrestrial system to the given particle. Okay. So what I'm going to do is I'm going to apply this down here. It's going to write it over first. I believe. No, that's what it is. My file here did not show the proper drop something off on the equation. Let me find out what it was to make sure. That's it. Notice there's a WX, WX, but there's nothing after the X. Uh, in equation 4.86. Oh, that's a typo. This book does have several typos. Maybe they meant to put a vector after that. Right. Keep it. So that's the same thing as VS equals VR plus omega. I was to, I think what they did was I took this and they multiplied both sides by r, is what I'm thinking. So now you have dt dr dt is v, dr dt is v omega, and right, that's what I think they did right there. But Vs and Vr are the velocities of the particle relative to the space and rotating set of axes, respectively. And omega is the constant angular velocity of Earth relative to the inertial system. Velocity relative to the space axes, velocity relative to the rotating axes. Second step, equation 4.86 is used to obtain the time rate of change of V. So now we have A S equals A R plus omega cross B E R D T R, because the property of the cross product is if you multiply it by a scalar, which is this is basically full scalar, you can multiply it by either one and it'll give you the same answer. So we have A R plus omega times V R. Now, hold up. They have the space for the right one. I wonder why. So this becomes S Why S and not R? It's a question I have about that one. But yeah, all of these are S. So I thought they were DT, DT, and that. But they're not. They're inserting VS. So let's back up. That was equation 4.86. So I'm applying 4.86 to R. 2. Which is 4.88 to 4.86 to VS. Right? So again, 4.86 is this. This to VS. And now we have AS equals, because that's both S. Now we have the V S over dt r plus omega cross V S. 3. Insert V S per 4.88. So now we have a R equals the V S dt R. You bring this to the next line. Omega the cross product with this entire thing. V R plus omega cross product R. So this equals the V S over dt R plus omega cross product V R plus omega cross product omega cross product R. So seeing how they're getting the 2 omega cross product VR. When you look at my cross product identities. So look this up really fast. Cross product identities. Have that right. A. So we have A cross product B plus C equals A cross B plus A cross C. So that's what I did there. Now let's say you have a cross product and another cross product. With a triple cross product. So we have A cross B cross C equals A dot C B minus A dot B C. So we have ABC, so ACB, ABC. So A stays first, and you swap which one is on the outside, and you subtract the one where the middle one is on the outside first. So this means I have a S plus omega cross V R plus omega omega dot omega times omega dot R times omega minus omega dot omega times so A is omega, so we have AA. B is omega, so we have B. T is R, so we have CC. Now, omega dot omega, what would that be? That would be the magnitude of omega. Would it be? Okay. T as another identity I can use. See if I have 2, 3 dot 2, 3. That's square. Eight. C. Hopefully the video is going fine. Right. Body rotating. They have that. And perhaps, oh, you know what it is? Because I didn't apply the DDT to the whole thing. All right, hold up. No, no, mind. We had to insert VS right there. Insert VS. And welcome who's watching. Let me know if you have any questions or comments. Okay. Think I see what I did incorrectly. Even though I may still need this. So let me back up here. So I'm applying 4.86 to VS. Should be an S here. So badly drawn S. So I'm taking DDT of all of that. So we have DDT. What I'll do, let me call this A. I'll call this B. Call this C. So if I also work with just A, we have DDT. And let me say, I'm going to just write this whole thing out very explicitly. 3. Insert VS from 4.88. So that means we have DDT of this. Yeah. Why did I do that for the first one? I think I should. So here's where it started. I'm gonna copy this right here. Put it there. This is still space, still equals, and so we'll back up a little bit more, and this will be my A, this will be my B, and I may need this a bit later. All right, so A, we have B, BT, and I'll just copy this down. That equals D, V, R, T, S, plus D, DT, this whole thing. And when you're multiplying a cross product with a scalar, we can treat the DDT like a scalar. That's the same thing as so I looking at the rule we set here, space, I think what I will do here is E, E, R, E, C, S plus, I'll distribute that to the R. So we have omega cross product D, R over DT, S. This is still just A, and this would explain why we had an extra one. It's actually only on the right side. Let's see. If I call this entire thing AS, dv dts. So we have that equals a equals a s. So this is the one where you insert on the left side here, dv here. All of this stuff is still just the left side. All of this is still a. As equals that. And missing an R. So the VRDT part, need another relation. So we have from up here, so this is a lot of substitution. We have what that means. So we can say let's copy this down. I'll highlight that I took this. I'm going to substitute it for VS. All of it stays the same. So we have this. It looks ugly, but this is actually equal. And perhaps, look back where I'm going. This is it. Going for AR plus 2 omega VS. Let me, that's from up there. Cross products. So if I said that this equals dv S over dt r plus 2 omega cross v s equals a s. And this is closer to what the book has. But this also equals the other side there. Oh, I think it's that either. I'll just come back to this another time. I'm not seeing how they're getting that exactly. So for now, I'll just copy that. Let me look one more time, just in case. This is true. Input VR. Yeah, I think that is what we're going for. I think what I need to do is, I see what I missed. This becomes aura when I substitute that in. 486 again. So it's not that. I mean, I need to apply 4.86 one more time. So try that. Input VS from 488. 4. Apply 4.86. Again, because we have VR, V space. It becomes VR, VR. This becomes D, V, VR over DT R, applying the formula. So on the other side, it becomes R over here. Plus omega cross the correction R, or just some correction. Well, it should be the same vector that it was the correction of. That'll be VR. This is starting to look better. So I applied 4.86. We have that. Distribute this to that. So now I have A R plus omega cross V R plus omega cross. I have B. Now the only thing about it is that there must be in the body space. Yes. It seems like it should be VS when I distribute that. Because there's the inertial there. Maybe I'm mixing that up. If this were R, it will give me my 2. And A. So what I'm thinking is this process, yeah, it should be applied to the right side. So I make this one adjustment, and I make this B. And let this come down. Have instead of A, we have plus omega plus VS. Thing on the left side stays the same. Right. I'll just ask about it. I'll just move on. So I'll just add another page after this. Maybe I'll come back another day and show you all what I end up with. I don't want to spend too much time on this. So I'll put AS equals AR plus 2 omega cross V plus omega is 4.89. So I'll make a note to come back to this. VS has been substituted from equation 4.88, and where AS and AR are the accelerations of the particle in the two systems. Finally, the equation of motion, which in the inertial system is simply which we're familiar with. inertial system, equation of motion, expands when expressed in the rotating coordinates into the equation, all right? Minus 2m omega cross v r minus m omega cross omega cross r equals m a r. This is 4.90. Hmm. So let me fill in the steps of what they did. So you have F equals ma in an inertial frame. I'm going to plug in this and this. So now I have F equals M, putting all of this as a S. So that gives me M A R plus 2M omega cross V R plus M omega cross omega cross R over S. So they subtracted everything into onto one side. So these two are going to go over there. So now you have the minus 2m omega plus VR. All of this is going to go over there. So now you have your minus mw cross w cross r. And they dropped the s. I guess because they put it on the left side. I guess it's just understood that the left side is for s. Now notice that the MAS. Okay, I have to put the S there because the S is on the A and the whole A is the whole thing. So all of that is AS with no sub. All right. All right, there we go. That looks good. To an observer in the rotating system, it therefore appears as if the particle is moving under the influence of an effective force F effective. Yeah. effective equals M-A R, which equals F minus 2M omega cross V R minus M omega cross omega cross R. This is 4.91. Let us examine the nature of the terms appearing in equation 4.91. The last term is a vector normal to omega and pointing outward. Okay. Formula of its magnitude is mw squared r sine theta. So let's look at this last term. So we're talking about this term here, m omega cross omega cross r equals m omega omega cross r sine theta. But they have m omega squared r. So perhaps did they use the triple? No, because we didn't get a dot product. Okay. So we have mr cross product omega cross r. So if the angle between these two is 90, we have that this equals m omega omega r sine. So I'll call this theta prime. So that equals m omega squared r sine theta. So that just means that so this makes sense. So this will be, these two are perpendicular to each other because you can get a cross product from them. And this is perpendicular to those two. So since R is perpendicular to W, then W has to be perpendicular to whatever that outputs. So in other words, these two are at a right angle to each other. So if omega is being a dot product of that, it'll have to be a right angle as well. Just from the nature of the right angle. And I guess technically it doesn't have to be a right angle, but we're going to extract out the right angle from it. So I can go ahead and call this angle between these two a right angle. Maybe I should try to draw this out geometrically. So I have a vector omega, and I have a vector r. And the dot product of these two vectors, I will call um, P, vector P. So vector P would be at a right angle to both of these. This is what I mean with the 90 degrees. So P, by the nature of the dot product, will be at a right angle to both of these. And omega, M omega, so this is M omega, which is just the omega vector scaled, because there's a M scaling the omega vector. So we can see that these angles are already in the right angle to each other. This angle here that are marked in blue, that is 90 degrees to MW by nature of the fact that P is a right angle to WR. So that means that this angle is theta prime in blue, and theta prime will necessarily be a right angle, which is the angle between these two. So since theta prime is going to be a right angle necessarily, because P is a right angle to both of those, these P is a right angle to MW, that means that I can call theta prime 90 because it's MW across P. Let me write that. MW plus P equals MW P sine 90 equals MW P. And this is what we have here because this is P. So we just end up with MWP. And then we can input what P is. And maybe I should add that as a step. Equals. And let me know if that's not clear, you who are watching. But this is what the book did to eliminate an angle. And now we know that this equals M omega omega cross R. We can apply the identity again. This WR sine theta times MR. So we have M omega squared R sine theta, but we don't necessarily know what um, the angle is between W and R. So this angle would be theta, is regular theta, and we don't know what that is. All right, so then you just leave that as theta. All right, that's easy enough. So that is pretty neat, I would say. So this equals magnitude. It will therefore be recognized that this term provides the familiar centrifugal force. It is the outward force, the outward fictitious force. It will therefore be recognized this term provides the familiar centrifugal force. When the particle is stationary in the moving system, the centrifugal force is the only added term in the effective force. So in other words, if you're stationary on the surface of the Earth, then only the centrifugal force from the spinning of the Earth is the only force you'll feel, notwithstanding the movement around the sun. But we're just talking about just the rotation. However, when the particle is moving, the middle term, known as the Coreolis effect, comes into play. All right. The order of magnitude of both of these quantities may easily be calculated for a particle on Earth's surface. Earth rotates counterclockwise about the North Pole with an angular velocity relative to the fixed stars. Right, so now we're getting into some interesting stuff. Coreolis and centrifugal magnitude on surface. Scroll too far. Right. So we have the Earth here. It is rotating this way. Counterclockwise relative to the stars. Omega equals, so let's see how they do this. Earth rotates once per 24 hours. So angular frequency second. So that's one rotation for 24 hours. So that's 2 pi degrees for 24 hours. So that's 2 pi divided by 24 hours. And 1 hour is 60 minutes. And 1 minute is 60 seconds. So we have that's 2 pi divided by 24 divided by 60 divided by 60. I'll calculate that really fast. So 24 divided by 60 divided by 60 equals 's wrong. Yeah, that's what I did. That's what I wrote my. Normally I do a shortcut here, by the way. This is good. I'm practicing and doing it in more detail to show you all. So it's actually times. So hold up, it's going in the wrong direction. The 24 times 60 times 60. All right, here we go. So that's 86,400 seconds. Now, I'm sure what they're doing with the 366.5 and 365.5 thing. Oh, I think they're taking into account that uh, the Earth has to make up for the leap year thing. Let me see what I get really fast. When I divide this, maybe I should just break out my actual calculator and doing the computer calculator. Tedious. We break out my actual calculator so I could just type it in really fast. Uh, that's pretty much what the book has without the uh 2, 7. Um, so 366.5, 365.5. Instead of 1 year, it's a little bit more than 1 year. It is taking into account the leap year. And to show you what I mean, like so the Earth is rotating around the sun. We'll make the sun here. Of course, not the scale, but we'll say the sun is very far away, so it could be the scale. I don't know how far You put the camera, no, it would still not be in scale. And so as the Earth is going this way, it moves here before it completes its full turn. So it has to turn a little bit more to compensate for that. So you can say one rotation relative to the stars is a little bit more for it to be facing the same direction, if I'm thinking about that problem. Or it's a little bit less. But it doesn't really matter. It's just a very small correction. I'll just ignore the correction for now. Maybe I can ask about it, but pretty sure. Yeah, I'll just make a note to ask about it just to be sure. Put that one there. And I'll put question. We have 366.5 divided by 365.5. So I'm sure it has to do with the fact that the Earth had to spin a bit more to catch up to the original spot, but I'll get more details on it. Where is my mouse? Here, the first set of parentheses gives the angular velocity relative to the radius vector to the sun. The quantity in the second parentheses, oh, they mentioned it. The ratio of the number of sidereal days in a year to the corresponding number of solar days is the correction factor to give the angular velocity relative to the fixed stars. Seems like it should be smaller than greater. Let's see what that difference is. 366.5 divided by 365.5, 1.0027. So relative to the fixed stars. Because we're spinning that way, we're rotating this way. I'll have to think about it. I'll just do it another time. It's not a big deal. With this value for W and with R equal to the Earth's equatorial radius, the maximum centrifugal acceleration is. So, what do we have? We have the sun is here, the Earth is here, and A is 1 AU on average, which is roughly or 6 e to the 11 meters. And we have centripetal acceleration equals v squared over r, which is what they're applying here. Oh, hold up. We're doing v squared r. Look up this formula. With acceleration. Yeah, v squared over r. So why do they have v squared times r? This could be a typo. Let me see what I get from this. This is r. Mm, I think they're using a conversion between this and so if I have This is angle phi. This is S. So if S equals phi r, we have phi equals S over r. Phi dot equals S dot over r. So we have S dot equals phi dot r that equals V. So V squared equals phi dot r squared, which equals phi dot r squared squared, which equals omega squared r squared. So they did this conversion. So that means that we have AC equals omega squared r squared over r, which equals omega squared r. So this is how they got that, the bastards. So they converted between the velocity, tangential velocity, this is to place the tangential velocity up in here somewhere. Right there. So that equals V. All right. And thank you for watching. Let me know if you have any questions or comments. I'll be happy to address. And now we see how we got this. And now we see how the book has the omega. So this equals, what did we have for that? And we could do it this way, but then we would have to calculate the uh, transition velocity, which is easy enough to do. I did that for you all 1 week when I was doing, I remember what I think I was calculating I don't know, we had a problem when we went over that. But let me plug this in. So I have 7.27 times 10 to the negative 5 second squared times this equals that times 1.496 e to the 11 meters. So let's see what we get. This times 1.496 to the 11 meters. We get 1.08 or 1.09 times 10 to the 7 meters per second squared. Put it in centimeters. And my number seems way too big. Hold up. Oh, I forgot the square. Oh my gosh. Erase this. So it's 7 point all of that squared times 1.4496 times 10 to the 11. All right. Still, my number seems different. Let's see what other detail we have here. So the angular acceleration I have matches very closely. I just didn't do the correction factor. It's off by what? 100th of a decimal. That's fine. 10 to the negative 5. And oh my gosh. I'm I was thinking about the solar system. I don't need this. Looking at the wrong distance. Even though they did use that to get rid of the what's we call them. This is not R. This is R. In case we need it later. R. And the Earth radius outward. This is little r from the center of the Earth. So let me look at the Earth's radius. Eventually, I'm sure I'll know all these numbers by heart because I'm starting to use them so often. Earth's radius. Uh, put this here. R equals 6378 kilometers. So this is the centripetal acceleration due to the rotation. Oh, that means I do need to, I mean, the process is the same, but really this will be the whole thing will be the Earth. Here. It will be R, and I can actually make this a little bit bigger. So this whole thing is the Earth. And the velocity is the uh, tangential velocity of the surface as it spins. There we go. So the math and physics is still the same. It's just a jump straight to a solar system view. This is the North Pole. All right, now we're on the same page. So we have this is R. So we have 6, 3, 7, 8 e to the 3 meters. All right. So let's see. This does what we need. 6, 3, 7, 8 times 10 to the 3. And that's what they have. I got this equals 3.37 10 to the negative 2 meters, which is 3.37. Oh, this meters per second squared. Centimeters per second squared. All right. So to make sure I'm clear, since I changed up a little bit, This is the Earth rotating this way. And this is a point on the Earth's surface. So as we spin in this direction, we're moving across S, a a line across the surface of the planet, which you could say is the arc of a circle. Come out of it as an arc of a circle. So the distance that you travel will be the amount that the Earth spins, which is the angle phi, times the radius of the Earth, which is r. So if you're standing on a certain part of the Earth spins a little bit. Person looking at you from outer space can say this person moved by this amount s due to the rotation of the Earth alone. And a person looking from outer space can look at you move and say, well, you moved from there to there due to the spin of the Earth. Took a certain amount of time. That'll be the velocity there. A certain amount of time it took you to move from this point to that point due only to being carried by the rotation of the Earth. So you can take that dynamic and say S, the amount of distance you move across the surface of the Earth. I'll draw this S a little bit better. Is, as we said, the angle that you move through times the radius of the Earth. Solve for theta, which is the angle that you're moving through. Take the time derivative of that because the angle is changing over time. S, the amount you move is changing over time. Solve for S dot, which is the velocity, how long you went, divided into how long you went over. Position divided by time. So now I have the tangential velocity, the velocity that I'm going through space due to the spin of the Earth, in terms of the angle that you're moving through. And the angle that you're moving through over time is the angular velocity, how much angle you move through over time. That's W. So now I have the tangential velocity due to the spin of the Earth in terms of the angle that you move through. And then I simply plug this equation into the centripetal acceleration equation. So now I have omega squared r squared over r. When r cancels out, we have the equation the book has, which is omega squared times r for the angular for the centripetal acceleration. So I plug in what my omega squared is from the spin of the Earth on rotation a day, the radius of the Earth. Now I get my centripetal acceleration, and I'll be caught up with the book as far as the centripetal acceleration of the Earth. At least a point on the surface of the Earth due to the rotation of the Earth. And they're relating this to gravity. So G is 9.81 meters per second squared. Why did they put it into centimeters anyway then? All right, so let's see what this is. So AC divided by G is going to be 3.37 times 10 to the negative 2 meter per second squared divided by 9.81 meters per second squared. So this is going to be 3.4 10 to the negative 3. So this is going to be 0.00344. This is going to be 0.3%. So that's how they got that the centripetal acceleration of that we experience, that we feel due to the rotation of the Earth, is only 0.3% of gravity. So that's a very small percent of gravity. So gravity is still 99.7% of what we feel, of what we experience as we stand on the surface of the earth is gravity, as far as centripetal acceleration. Which is why we don't go flying off into space. Uh, just from the spin of the earth. So small. Technically, yeah. So we're spinning around the earth. So this amount of acceleration is kind of like if you uh, have something on a string and it's spinning around. If you let the string go, it flies away. So the earth is basically trying to throw us off from its spin. It's like we put that in terms of centripetal acceleration. Right, let's just keep going. While small, this acceleration is by no means negligible. However, the measured effects of gravity represent the combination of the gravitational field of the mass distribution of Earth and the effect of centripetal acceleration. It has become customary to speak of the sum of the two as Earth's gravity field as distinguished from its gravitational field. One thing I'm unclear about is we're being held to the Earth because of gravity. So it seems like centripetal acceleration, it seems like this force would actually be throwing us off rather than holding us up, holding us in. That's the acceleration that we have. That's just what it is due to the spin of the Earth. Hmm. Right. Let's keep going. The situation is further complicated by the effect of the centripetal acceleration in flattening the rotating Earth. The Earth were completely fluid. The effect of rotation would be to deform it into the shape of an ellipsoid whose surface would be an equipotential surface of the combined gravity field. The mean level of Earth's seas conforms very closely to this equilibrium ellipsoid, except for the local variations of wind and tide, and defines what is called the geoid. Except for effects of local perturbations, the force of gravity will be perpendicular to the equipotential surface of the geoid. Accordingly, the local vertical is defined as the direction perpendicular to the geoid at a given point on the surface, not the actual surface of the Earth. Phenomena that occur in the vicinity of a particular spot on Earth, the centripetal acceleration terms in 4.91 can be considered as swallowed up in the gravitational acceleration g, which will be oriented in the local vertical direction. The magnitude of g, of course, varies with the latitude on Earth because of the spin, it seems. The effect of centripetal acceleration and the flattening of Earth combine to make g about 0.52% less at the equator than at the poles. That's what I was talking about. I think this book doesn't necessarily explain things very well sometimes, even though it could just be my understanding of it. But like I was saying, it seems like we're being thrown off the Earth because of the spin. Therefore, G is less at the equator because you're getting thrown off. Centripetal acceleration. The centripetal acceleration is throwing us off. Gravity is pulling us down. So because of centripetal acceleration, which is, you could say, in the positive direction, and Earth is pulling in the negative direction, we end up a bit lighter at the equator because the centripetal acceleration would be greater. So I guess you can say, let's see, so I calculated it at the equator basically. If you're at a higher latitude, let's say you're here, the radius will be some scalar of r, and it'll be less. So eventually it's zero. At the pole, A is zero, alpha is zero. So there's no radius in the direction of the spin. So you will have no centripetal acceleration at either of the poles. So at the poles, you'll experience the full polar gravity because you're just basically spinning in place. You're basically just going like this if you stood on the surface of the Earth, and the Earth is spinning this way, but you're like right there on the center. You're not moving. But standing here on these sides, you get any full centripetal acceleration, and that lessens your gravitational pull by 0.53%, which I'm not sure how that got 0.53 when the acceleration is 0.3%. Oh no, we'll keep going. Incidentally, the centrifugal force on a particle arising from Earth's revolution around the sun is appreciable compared to gravity. That's interesting. But it is almost exactly balanced by the gravitational attraction of the sun. That is neat. If we analyze, so in other words, the Earth is going around the sun, and there is some centripetal acceleration from this motion that's throwing us off, but at the same time, the sun is pulling us in, and these balance enough to where we're all right. If we analyze the motion of the solar system from a frame rotating with Earth, it is, of course, just the balance between the centrifugal effect and the gravitational attraction that keeps the Earth and all that are on it and the sun separated, right? So the reason why we're not as a whole crashing into the sun or flying out into space is because those things are balanced, which makes sense. An analysis in a Newtonian inertial frame gives a different picture. As was described in section 3.3, the angular momentum contributes to the effective potential energy to keep the Earth in orbit. Okay? So the Earth has a potential from where it's situated. It doesn't fall down. And the acceleration of the Earth around the sun contributes to that potential energy. Which makes sense. If it wasn't spinning, it would be closer to the sun. Like how the analogy that I use with the ball spinning around a spring. The faster you spin, the more this tugs out, but your string is pulling more to stop it from flying away as it spins at that particular distance. The Coriolis effect on a moving particle is perpendicular to both omega and v. So just think about that. So we have the Earth. We have velocity going this way. This is omega. Perpendicular to both. So if an object is moving along the surface of the Earth this way, let's do up here this way. Coreolis, of course, must be this way. Coreolis v omega. But it's not perpendicular to the. Okay, I'm gonna have to let them explain this. I'm not seeing the direction of that. Right now we're on page, what? 76. Coreolis is perpendicular to omega, and Coreolis is perpendicular to V. Give us an asterisk. Let's see what the asterisk says. From here on, the subscript R will be dropped from V, as all velocities will be taken with respect to the rotating coordinate axis only. All right? So basically, the axis of the Earth is the default axis that we're using. The Coriolis effect on a moving particle is perpendicular to both the angular velocity and the velocity of the particle. In the northern hemisphere, where omega points out of the ground, the Coriolis. Oh, hold up. How did I forget that? I was just saying that earlier that omega, that centripetal acceleration, is countering gravity and throwing us into space, or trying to. So this is omega, and sorry, hold on. That's a spin. This is omega. Omega. This is right angle to the surface of the Earth. This image for omega points out of the ground. The Coriolis effect tends to deflect a projectile along the Earth's surface. So velocity. So velocity is here. We know that the Coriolis is going to be perpendicular to both. Along the surface of the Earth is going to be perpendicular to omega. So it's likely to be either this way or this way. All right, let's keep going. The northern hemisphere, the Coriolis effect, 2m omega plus VR. I noticed they swapped the location of the V, by the way. Did you all notice that? So here, omega is first. No, and then V is first. I guess it's a typo, because that'll give the negative direction, unless they're saying that it is the negative direction. Is to deflect a projectile shot along the Earth's surface to the right of its direction of travel. In the northern hemisphere, it is the one to the right. So it'll be this way, across the surface of the Earth. That's Coreolis in the northern hemisphere. That makes sense. Because closer to the equator, the spin is faster. And in this example, I'm drawing velocity going towards the north where the lateral spin is slower. So the lateral spin of the particle will be faster than the part of the Earth where it's going to. Therefore, it'll appear to go to the right where it's going faster. And it seems like the two uh, uh, things combined, the spin and the motion, will combine to make this a right angle as well. So it's a right angle to omega and a right angle to each other. To the right. The Coreolis deflection reverses direction in the southern hemisphere and is zero at the equator where omega is horizontal. And it's not necessarily out of the Earth directly. It must be at an angle. The magnitude of the Coriolis acceleration is always less than 2mv, is about 1.5 10 to the negative 4v. Got the Coriolis term one more time. I should write that. Coriolis acceleration less than 2 omega v, which is about equal to 1.5 e to the negative 4 v. Right? So this is what I was trying to draw earlier. So the book actually gives us the image. Should redraw it here. We have v naught v. This is v cross omega. Omega. So omega z, omega is going out the page. At least, up from the surface of the Earth, I guess just to see. The omega has crossed the Earth. Perpendicular to omega and v. It's perpendicular to omega and v, then it's v cross w. And I have the right idea to combine the combination of the two. I'll just call this Coriolis movement. So a velocity of 10 to the 5 centimeters per second, roughly 2,000 miles an hour, is 15 centimeters per second squared, or about 0.15 g. Normally, such an acceleration is extremely small, but there are instances when it becomes important. To take an artificial illustration, suppose a projectile were fired horizontally at the North Pole. The Coriolis acceleration would then have the magnitude 2wv, so that the linear deflection after a time t is wvt squared. The angular deflection would be the linear deflection divided by the distance traveled. Theta from pole is omega v t squared divided by vt, which equals omega t, 4.92. Which is the angle Earth rotates in the time t. That makes sense. Because if it's coming from the pole, it has no sideward motion. So however far it travels, the Earth would move under that. Physically, this result means that a projectile shot off at the North Pole has no initial rotational motion, and hence its trajectory in the inertial space is a straight line. The apparent deflection being due to Earth rotating beneath it. Well, that's what I just said, so I'm getting an idea. An idea of the magnitude of the effect can be obtained by substituting a time of flight of 100 seconds, not unusual for large projectiles, in equation 4.92. The angular deflection is then of the order 7.7 times 10 to the negative 3 radians of about 0.4 degrees, which is not inconsiderable. Clearly, the effect is even more important for long-range missiles, which have a much longer time of flight. The Coreolis effect also plays a significant role in many oceanographic and meteorological phenomena involving displacements of masses of matter over long distances, such as the circulation pattern of the trade winds and, of course, of the Gulf Stream. The full description of these phenomena requires a solution of complex hydrodynamic problems in which the Coriolis acceleration is only one among many terms involved. It is possible, however, to give some indications of the contribution of Coriolis effects by considering a highly simplified picture of one particular meteorological problem, the large-scale horizontal wind circulation. Masses of air tend to move, and other things being equal, from regions of high pressure to regions of low pressure, the so-called pressure gradient flow. In the vertical direction, the pressure gradient is roughly balanced by gravitational forces, so that it is only the horizontal plane. It was only in the horizontal plane that there are persistent long-range motions of air masses, which we perceive as winds. Okay? The pressure gradient forces are quite modest and comparable in magnitude to the Coriolis effect acting on air masses moving at usual speeds. In the absence of Coriolis effects, the wind directions would ideally be perpendicular to the isobars, as shown in figure 414. I don't get the gravity part of it. Masses of air tend to move, other things being equal, from regions of high pressure to regions of low pressure. Makes sense? The so-called pressure gradient flow. In the vertical direction, the pressure gradient is roughly balanced by gravitational forces. Okay, so in other words, gravity is pulling things down so that the lower part is more higher pressure, but gravity keeps that static generally, so that it is only in the horizontal plane. So if you have higher pressure here and lower pressure down there, we're going to move laterally as wind, but vertically we have a higher pressure down here and it remains higher pressure because it's not going to flow up because of gravity holding the air down. Okay, that makes sense now. The pressure gradient forces are quite modest and comparable in magnitude to the Coriolis effect acting on air masses moving at usual speed. In the absence of Coriolis effects, the wind direction would ideally be perpendicular to the isobars as shown in figure 4.14. However, the Coriolis effect deflects the wind to the right of this direction in the sense indicated in the figure. The deflection to the right continues until the wind vector is parallel to the isobars, and the Coriolis effect is in the opposite direction too, and ideally just balances the pressure gradient force. The wind then continues parallel to the isobars, circulating in the northern hemisphere in a counterclockwise direction about a low center of pressure. In the southern hemisphere, the Coriolis effect acts in the opposite direction. In the cyclonic direction, the flow around a low center of pressure is clockwise. Such a wind flow deflected parallel to the isobars is known as geostrophic wind. In this simplified picture, the effect of friction has been neglected. At atmospheric altitudes below several kilometers, the friction effect of eddy viscosities become important, and the equilibrium wind direction never becomes quite parallel to the isobars, as indicated in equation 4.15. Another classic instance, let's take a look here, idealized cyclone pattern in the northern hemisphere. Doesn't seem much different. Another classic instance where Coriolis effect produces measurable effect is in the deflection from the vertical of a free-falling particle. Since the particle velocity is almost vertical and omega lies in the north-south vertical plane, the deflecting force 2mv cos w is in the east-west direction. Thus, in the northern hemisphere, a body falling freely will be deflected to the east. That's interesting. Calculation of the deflection is greatly simplified by choosing the z-axis of the terrestrial coordinate system to be along the direction of the upward vertical as previously defined. If the y-axis is taken as pointing north, all right, so this is something to note. So z-axis is vertical from surface, y-axis north, so I'll also draw the earth. This would be z. This would be y. This is the North Pole. And the frictional effect of the atmosphere is neglected. Then the equation of motion in the x-east direction is the x-axis is going in the direction of spin. So F equals m a equals m v squared x over dt squared, which equals right. So we just take the Coriolis force directly from the equation and put that in for the acceleration. Um, setting for the force is the Coreolis force. Right. All of these terms are forces. Force is kilograms meters per second squared. So this must give me meters per second squared. So this equals negative 2 m omega vz sine theta, and this is 4.93. Seems like an important equation, but theta is the colatitude. Right. The effect of the Coriolis effect on Vz will constitute a small correction to the deflection, which itself is very small. Hence, the vertical velocity appearing in 4.93 may be computed as if Coriolis effect were absent. Simple enough. The integral of this is, so dx, no, dz over dt equals gt. So dz equals gt dt. Integrate both sides. So integrating for t. Oh, did it solving? Okay. Z equals 1/2 g t squared plus z naught. You know, I'll just call that 0. So 2z equals gt squared. T squared equals 2z over g. So t equals square root of 2z over g. With these values, equation 4.93 may be easily integrated to give the deflection as, okay, we're saying that m d squared x over dt squared equals negative 2m omega bz to theta sine theta. We have uh, and we're going to cancel. And now go dv equals negative 2 omega vz extra 2 there. sine theta dt. So v dx over, let me skip a step. We'll integrate both sides. They say it's easy, but we'll see. We have negative 2 omega vz sine theta t plus v naught, which we'll call 0. So then we have dx over dt equals that. So we have dx equals negative 2 omega vz sine theta t dt. We have x equals negative omega vz sine theta t squared. Hmm. I'm plugging my VT first. I have to do that before I integrate. So we have dv for dt, because dx dt is v, equals negative 2 omega gt sine theta dv equals negative 2 omega gt sine theta dt, which equals, if I integrate both sides, negative omega g t squared sine theta plus v naught, so we'll call 0. We have v, so dx equals negative omega g t squared sine theta dt. So I integrate both sides. So we have x t equals negative 1/3 g t cubed sine theta plus x naught, which I'll call 0. So I left off my omega. Root to 1/3 omega g cubed. All right, so we have x equals. I noticed they dropped a negative. Either they dropped a negative, or I should have done something to get rid of a negative. Cubed sine theta. So this is what the book has, and that was an easy integration. 3g over 3 t cubed sine theta, or x equals negative wg over 3 2z over g 3/2 sine theta. And let's see what they do here. We want to move the g into the two z over g g2 over 3 3 over 2 sine theta. So this equals negative omega over g. And oh, and it's in the denominator. So it's actually 2/3 when it's in the denominator. See, I made a mistake and wrote a g there instead of 3. So I'm going to move this in the denominator, which makes it negative 1. Let me write this separately. So g equals 1 over g. And this equals 1 over 1 over 1 over g, 2/3. This is 3 over 2, which equals 1 over g, 3 over 2, 3 over 2. I'm still not getting a regular g here. And you look back to when I inserted it. It should be 3 over 2, or maybe not. Let me think. Negative 1. Right, I think I see where it is. They're not flipping the g. They're keeping it as a negative, and then it balances out. So g is 1 over g to the negative 1. And this equals 1 over g to the negative 2/3. This is 3, 2 on the outside. So this will be a negative 2/3. So this will be 2z over g to the 1/3, 3 over 2. And this is the same thing as negative omega over 3 to z over g 1/3 cubed at 1/2. So this becomes negative omega over 3 And now we have the 1/2 is square root. So we have 2z to the third. And then we have g. All right. And this equals deflection. All right. An order of magnitude of deflection can be obtained by assuming theta is pi over 2, corresponding to the equator, and z is 100 meters. The deflection is then roughly 2.2 centimeters. The actual experiment is difficult to perform as a small deflection may often, as the small deflection may often be masked by the effects of wind currents, viscosity, or other disturbing influences. All right. It is easy to show using increased 493 that a particle projected upwards will fall back to the ground westward of their original launch spot. This can show that a particle will fall westward if it's shot straight up. Coreolis. I was looking at the asterisk that time, by the way. More easily observable is the well-known experiment of the Foucault pendulum. The pendulum is set swinging at the North Pole in a given plane of space. Then its linear momentum perpendicular to the plane is 0. And it will continue to swing in this invariable plane while Earth rotates beneath it. To an observer, on Earth, the plane of oscillation appears to rotate once a day. At other latitudes, the result is more complicated, but the phenomena is qualitatively the same, and detailed calculation will be left as an exercise. I'll do that. All right, last part of this. Effects due to Coriolis terms also appear in atomic physics. Thus, two types of motion may occur simultaneously in polyatomic molecules. The molecule rotates as a rigid whole, and the atoms vibrate about their equilibrium positions. As a result of the vibrations, the atoms are in motion relative to the rotating coordinate system of the molecule. The Coreolis term will then be different from 0 and will cause the atom to move in a different perpendicular to the original oscillation, in a direction perpendicular to the original oscillation. Perturbations in molecular spectra due to Coriolis effects thus appear as interactions between the rotational and vibrational motions of the molecule. Down. All right. So that was that. We're done with this chapter. On to chapter 5. So, as promised, we got through the entire section, and this will replace my stream tonight, as I'll be out and about. I'll make a note of that in my post, and I'll see y'all next week, if not sooner. Like, subscribe if you haven't. Join Discord. Let me know if you have any questions or comments in the comment section. Thanks for those who popped in. Thanks again, Aaron, for dropping a line. And you all have a nice one.